So we are doing orthogonality in this section 3.3. Does anybody know what that means if I say that something is orthogonal? Yeah, it is. It's perpendicular. So we have discovered quite a lot about our vectors. We know how to do the dot product. We know how to find the angle between two vectors. We know how to find the norm of a vector. So we've got a lot of things going on. One other thing we also want to know is whether or not vectors are perpendicular to one another, or if a vector is perpendicular to a plane or to a line. So this is something that's a very, very important concept. One thing you want to pay attention to, hint, hint, is that the zero vector, does everyone remember what that is? So if you have the zero vector, that's going to be orthogonal to every vector in real space. So just by definition there. So what? Yeah, so part of this definition one, you just want to also realize that the zero vector, it is going to be orthogonal to every vector in real space. So you never know when that might pop up as a true-false question.
Are vectors used in the not real space?
Yeah. We're only dealing with real space here, but you could obviously, yeah. So it could definitely get more complex. We won't get to that in this class since it is an intro basic course here. So here we're going to be looking at whether or not vectors are orthogonal. Can anybody guess what we're going to do to tell? Yes, and what does it got to equal? It's got to equal 0 if they're perpendicular, right? We learned that from last section, so don't forget that. Something that you want to also realize with this example one, that's a really, really important point. Can anybody guess what they're trying to demonstrate to you with this last portion? We're here, they have the dot product of ij, ik, jk. Assuming this is in three-dimensional space.
Vectors are all perpendicular to each other.
Yeah, but what kind of unit vectors? Standard unit vectors in particular. So all of your standard unit vectors are going to be perpendicular to one another. So there's some important points there with that example one. Okay, so I also have on here, don't forget, I've got a little cheat table here about your different values for your cosine. So you might want to check that out once again, put it here too. Okay, so we know how to do our dot product to be able to tell if two vectors are orthogonal or not. Okay, so that should be something you should be able to do on your own, example one. So here's the other important point that they make is that, you know how we always talk about the slope of a line? And then you might think of, okay, we have a plane and it's going to be at a certain incline. Well, one of the ways that we're going to describe that slope or describe that incline is going to be to find the normal to that particular line and the normal to that particular plane. So that's going to be another way to describe the slopes or inclinations of lines and planes. So just take that into account there. So the way that we are going to specify the slope and inclination is to use a non-zero vector n that is going to be called a normal. So it's not to be confused with a norm because that's just going to be your length or your magnitude. Now we're actually finding a non-zero vector n. So they are going to be using pretty regularly the notation of n. And now you're going to be finding a normal. And so this vector n that's a normal, it's going to be perpendicular to whatever line or plane is in question. And so by finding that normal, you have yet another way to kind of define the slope of that line or define the inclination of that plane. So we are going to be looking at that. Now here we call this the point normal form of an equation to be able to help us figure out what that normal is. And so this is going to be the point normal equation that we're going to use for finding the normal to any line that includes this point P0 or any plane that includes this point P0. So just keep in mind your terminology here. This particular notation here, so it's going to be the dot product here, you set that equal to 0. That is going to be the point normal form of a line or plane. Now, we can actually break that down into the component form of a line or plane. And so here is going to be your component form of being able to identify your normal. So here now, instead of just, having this short annotation here that we've used to see this written like this, now here we're actually doing it in terms of a point's components, and here's a plane's components here on this last one. So you'll notice that this one is in 2 dimension. It's got x and y. Here we've got 3 dimensions, x, y, and z. So these are going to be called your component form of a line or plane. This is the point normal form of an equation. This is going to be your component form of an equation of a line or plane. So keep in mind, like I said, that terminology. So let's see what other stuff we got going on here. So lines, we're going to use normals to kind of determine our lines. We're also going to use normals to determine our planes. So these are all laid out separately. You're going to want to take a look at this equation. You want to make sure that you take a look at it. You want to notice that this is all set equal to 0. Same thing for your planes. This is all going to be set equal to 0. So important things to notice here. So here is going to be where you're going to want to look at example 2, because if you're looking at your point normal equations, you would want to easily be able to recognize what is your points that you can get from this equation. You want to be able to easily derive your normal from these equations. So let's check out example 2 here. Let's see if we can get it up on the book here. Ooh. Example 2, where'd you go? There it is. Okay. So it's really simple to kind of point out what is the normal. So if you're given an equation like this, as long as it's in this format, so keep in mind you need to have it in this format. This one's going to be for a line, right? Because this is in 2 dimensions, x and y. This one's going to be your equation for a plane because you have x, y, and z. So here, if you look at example 2, we can easily see that this equation is going to represent a line through the point 3, negatives, and -7. So I think we can see that right here. We're getting the 3 from here for the x, and we're getting the -7 here for the y. But here it's really easy to pick out the normal. So the normal is going to be 6 and 1 here. So if you look at your previous equations for your lines and your planes, your normals are going to be defined by these coefficients a and b. And if you look at the plane, here we've got another one, a, b, and c. So it's really easy to kind of pick those out. So if I were to give you a line with this equation here, you'd be able to easily pick out the normal and a point going through it. So check out example number 2. Now, what do you notice then about this theorem 3.3.1? So here's another way of kind of writing what I just said. So it says here, if a and b are constants that are not both 0, then an equation of the form ax plus by plus c equals 0, that is going to represent a line in 2D space with a normal n with the components ab. So here you're picking out ab to form your normal. What do you notice is left out?
C.
Yeah, c. So just realize, you want to pay attention to this, c is left out. You're able to pull out the normal. It's going to correspond to your unknowns, but you want to make sure that your equation is written in this format. You have to set it equal to 0. So your constant is going to be on the same side of the equation as your variables. So here your n is going to be your ab, just your ab. Here, if we're talking about a plane, then your normal is going to just be a, b, and c. It is not going to include this d here.
So to sum it up, basically, it's just saying the normal is in 1 dimension less than the equation.
Yeah, so and you're not going to include just a constant. So you're just going to pull out those coefficients in front of your unknowns here. You do not include this extra constant. So wanted to make sure that you recognize that. But it's really easy to pick out the normal for this kind of stuff. So you'd want to go ahead and check that out. Let's see here. What's another one? Oh, yes. Also, please realize you want to remember kind of back to your previous chapters, like here when you've set ax plus by equals 0, or you set ax plus by plus cz equals equals 0. Those are going to be homogeneous equations where those are set equal to 0. So don't forget that terminology from earlier.
Is it pronounced homogeneous or homogeneous?
I've heard it both, in all honesty.
I had a professor correct me and say it wasn't homogeneous. So,
Oh, it's homogeneous?
yeah.
Yeah. Yeah. I mean, I think it's been pronounced both ways so much that, you know, you can hear it kind of either way. A lot of times you hear more homogeneous when you're talking kind of with genetics.
That makes sense.
But, you know, yeah,
That way. Okay.
yeah.
Homogeneous and biology.
Yeah, so, I mean, I've heard it both ways and all.
Seriously, just sounds more homogeneous.
Like, it's all mixed up. So the other thing that we're going to look at really quickly, so there's going to be some examples that we're going to skip in this chapter. But one other thing that I do want you to know about are these orthogonal projections. What? So you may have done this before. Dun, 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 let me get to it. So I have some extra slides in there for you if you want. Okay, so if you're going to be doing an orthogonal projection, here's another application that you might actually want to do. So if you're going to do an orthogonal projection, you might want to decompose a vector u. So here we've got it here. And you might want to decompose it into a sum of two vectors. Okay? So you might have two vectors that you want to decompose u into. So here's what happens with orthogonal projections. You are basically, from the tip of u, you are going to drop a perpendicular from the tip of u. Is this not working? Dang it. Come on. Don't get out of me now. No. Okay. From the tip of u, you're going to drop an orthogonal perpendicular to your tip of u, and you're going to drop it all the way to a line that goes through A. And so where that hits A, we are going to denote that W1 in this text. Okay? And then the other vector that we're going to decompose it to is going to be this other vector W2. And then this one is going to be perpendicular to W1, and we're going to call this W2. Now, here's the deal with this W1. So W1 is going to be a scalar multiple of this line A, this line through A. So here, if we look at this picture, what would you kind of estimate W1 is here? Like if we said A ends right here. Yeah, we might approximate that here. W1 equals about a half A. But that's not always the case. So here, like this first picture A, we see that W1, if you drop from the tip of U and you drop it straight down to the line through A, W1 here is roughly about half A. Here, if we have this longer U and we drop it down, this W1, we'd probably say it's about 2A. Here, if we have it where U is in the opposite direction and we go from the tip of U and we drop it down to a line through A, we'd probably say that, I don't know what you guys think. Maybe this is like negative 2A then for W1. So just realize that W1 is going to be some sort of scalar multiple of A. And then you're going to have your other W2 vector that you're going to form that's going to be perpendicular to your W1. So here we come to our theorem 3.3.2. We have if U and A are vectors in Rn, and if A does not equal 0, then U can be expressed in exactly one way in the form U equals W1 plus W2, where W1 is a scalar multiple of A and W2 is orthogonal to A. So keep in mind this theorem 3.3.2. All right, so let's go ahead and we'll go to the next one here. So we looked at these three different cases, so definitely check out this diagram and kind of visualize for yourself that W1 is going to be a scalar multiple of A. All right, so now that we've decomposed our U down into those two vectors, W1 and W2.
W2's orthogonal scalar multiple.
Yeah, so this W2 is going to be orthogonal to A. So if you see these pictures? Okay, so if we have this vector U, we're simply going to go from the tip of U, we're going to drop it all the way down to some point along A. And that's going to give us our W1. And then our W2, or other vector that U can be decomposed into, that one's going to be orthogonal to A. So here, keep in mind that U is going to equal W1 plus W2. And then keep in mind that W1 is going to be some sort of scalar multiple of A. Does that make sense? Okay. So then they have where they want you to be able to calculate these things. And so they've given you this as an important paragraph here. So vectors W1 and W2 in the projection theorem have associated names. So you're going to want to make sure that you know these associated names here. The vector W1 is called the orthogonal projection of U on A, or sometimes the vector component of U along A. And then the vector W2 is called the vector component of U orthogonal to A. So you're going to want to read this a couple times, kind of get that terminology down. So if we want to actually solve for W1, we're going to be able to commonly denote that by this symbol that we say projection of A. So here, W1 is going to be the projection of U on A. So it's going to be denoted this here. So you have this like spelled out kind of shorthand for projection. And they have the subscript A and then U. And then your W2, because your U equals W1 plus W2, your U minus W1 is going to give you what your W2 is. So those are going to be, and I'll go ahead and write these on here on the slide real quick. So here, so W1 is going to be that projection of U onto A. And then we've got our W2 is going to equal U minus W1, and that's going to equal U minus all of this denoted. So you're going to want to look at these equations 10 and 11. And so here, basically, you just want to look at example 4. And here they've gone ahead and they've given you U and they've given you A. And so now you're going to be decomposing that vector U and you're going to figure out, okay, what is my W1 and my W2 from here? But you're going to use the projection notation for those here. So we will look at, you want to make sure that you look at example 4. That's going to be a big one. Now, here's the ones I did want to make sure that you knew that we're going to be skipping. So we are going to be skipping, because they rely on knowledge from past chapters, we're going to be skipping example 5, 6, and 7. So if you have a vector, going vector U, simply going through from the tip, and you're dropping it down to a point going through a vector A. Wherever that might be, that's going to be your W1. Now, like I said, W1 is going to be some sort of scalar multiple of A. Then your other vector, your W2, that U is decomposed into, it is going to be orthogonal to A. So as you can see the right angle here, right? So we are now trying to decompose that U into two vectors. So U is going to be the sum of W1 and W2. And then we've now learned all these handy-dandy things in order to calculate what those W1 and W2s are. So please make sure that you look at formulas 10 and 11 here, and that you know what are the names for W1 and W2 in terms of projections. So just to go over it one more time, W1 is going to be called the orthogonal projection of U on A. W2 is called the vector component of U orthogonal to A. And so this first one, formula 10, that's going to be how you solve for W1. And then this second one is going to be how you solve for W2. And so you've seen all this before. So we know how to do the dot product. We know how to take the norm. So you should be able to calculate those from these equations. So here with 4, they had let U equal the components 2, -1, 3. We have A is 4, -1, 2. It says find the vector component of U along A and the vector component of U orthogonal to A. So you should know by those terminology that what are they asking you to solve for? So you're going to be able to determine those vectors which U can be decomposed into. So this would be a method for decomposing U, like I said, into into W1 and W2.